Good morning to all. Welcome to lecture number 13 of Signals and Systems. To summarize about the previous class, we started to understand what's the meaning of signals and what is the meaning of system, and we could understand few of the properties of the system, and also we listed out six properties of the system, out of which four we could cover in the last session. So in today's session, we will be covering the rest two properties of the system, and we shall look some exercises and we'll conclude the chapter number 1. So quickly we'll go through the PPTs. I'm sharing my screen. Welcome you once again for lecture 13 and the last lecture of chapter number 1 of Signals and System. Topics covered in this lecture are properties of the system, in which we will be focusing on time invariance and linearity properties, and we shall look some of the exercises, and then we will conclude the chapter number 1, that is introduction to signals and systems. So to begin with, the time invariance is a property number 5. That is what we are focusing right now. The time invariance is something related to time. A system is said to be time invariant if the time delay or time advance of the input signal leads to an identical time shift in the output signal. The meaning is your system should be time invariant. It is recommended to be time invariant. Means whatever changes you do at the input in terms of time, the same identical changes should happen at the output signal. That's the meaning of time invariance. Or to put it in another way, the time invariant system responds identically no matter when the input signal is applied. For example, let me take some non-technical example. Today, if you switch on the computer or your TV, in the fashion how it switches on, in the same way, tomorrow also if you switch on the TV, it should respond in the same way. Then we call it as time invariant. For example, if you switch on your TV today, and if it is switching on, and if tomorrow if you try to switch on your TV, and if it tries to switch on only the volume, not the screen, then it is not a time invariant. It is varying according to the time. The system which does not vary according to the time, with respect to the time, such a system are called as time invariant, and it is recommended for a system to be time invariant. And here we write the time invariance representing a time delay or time advance with the time shifting property. S raised to T naught is nothing but based on T naught, either time will be delayed or time will be advanced. It is dependent on S raised to T naught. It's a shifting operator. H being the shift or system operator. Okay, so I apply the time shift and then I apply it to the system. So whatever output I get, same thing if I apply the input to the system and whatever output I get, then if we apply the time shift, both should not change. That is H S T naught is equal to S T naught H. If this is commuting, we call it as H and S T naught must commute with each other in order to call it as time invariant system. If this satisfies, then only we call it as time invariant. I'll write it here. The system is time invariant if and only if a system operator H and time shift operator ST naught must commute with each other for all T naught. Means irrespective of whether my input is fed directly to the time shifting operator and then to the system operator, or first to the system operator and then time shifting operator, both should result in the same equivalent results. Then only we call it as a time invariant system. You can see here time shift operator ST naught preceding operator H. This is preceding to H, and the next one time shift operator ST naught following operator H. ST naught is following operator H. These two situations are equivalent provided that H is time invariant. If H is time invariant, then only these two things will give you equivalent. If it is time invariant, if if it's a time variant system, I'm speaking about time variant, then H s raised to t naught will not be equal to s raised to t naught h, because it's a time variant and this is time invariant. Remember this. So we shall consider a CTS domain or continuous time signal wherein y1 of t is equal to h of x1 of t. I am considering the first block diagram. Just check here. y1 of t, let me call it as y1 of t, or else I'll not take this. One second. Let us not have confusion. This one. What is y1 of t? y1 of t is h of x1 of t. That's what I'm writing here. H of x1 of t. Then y1 t minus t naught. How to write it? It can be written as shift. I'm shifting it. How to write the shift? Representation, denotation. It's a shift operator. S raised to t naught. And if I write y1 of t, so these are the two things that operations we are making. H being system operator, S being shift operator. Let me call it as 1 and let me call it as 2. And so I substitute y1 of t, 1 in 2. So what happens? This is h of x1 of t. If I open the flower brackets, it will be st naught h x1 of t. So this I could get by block diagram 2, which was in previous diagram. Let me call it as block diagram 2. This is block diagram 1. In a similar fashion, if I do apply for block number 2, block diagram 2, then what happens is x2 of t is equal to x1 of t minus t naught. Just check here. This one. What is x2 of t? It is a shifted version of x1 of t. x1 of t minus t naught. That is what I'm writing. This I call it as number 1 now. Next. What is y2 of t? y2 of t is h of x1 of t minus t naught. That is what I write. y2 of t is, I am applying a system operator. My input is x1 of t minus t naught now. This is what is a input. This I call it as 2. So this x1 of t minus t naught means what? This is s raised to t naught x1 of t. That's the meaning. Or else I can write h s t naught x1 of t. You just check. This I got from block diagram 1. Just compare these two things. Let me change the ink. You compare these two things. These two things will be equal only if st naught h is equal to h st naught. Okay, so this is a condition for time invariant system. TIS, let me call it as TIS, time invariant system. I hope there are no doubts. Okay, so let me proceed in the similar manner for discrete time. For discrete time too, it is in the same fashion. It is in the same fashion. Let me write it here. Let me take an example directly. So what we are doing here is we are having a DTS signal, and for DTS signal we have described some system operator y of n is equal to r raised to n x of n. This r raised to n is a system operator here actually. Whether it is time invariant, that we need to check. Let me check it here. So for that I will take the diagrammatical explanation. This is input. Let me call it as for input. What is h here? H is r raised to n. Let me call it as h. And we will shift it and check. We'll shift it and check. It is not t here. It is a discrete time. That's why n I am writing. S raised to n naught. This will result in y1 of n. In the other way, if I interchange it, how do I write? X2 Fn, I apply the input directly to S raised to n naught, and then I apply to system operator. What is the system operator here? R raised to n. Then it will result in, consider that y2 Fn. Now let us check y1 and y2 are equal if x1 and x2 are equal. That is what we need to check. So what happens here? If I supply x of n as an input, then what happens? Let me change the ink for your understanding. What is output we get here out of this? R raised to n x of n we get. And after that, if we try to shift, what happens? This will result in, so n naught, shifting happens wherever n is there. Replace n with n minus n naught. R raised to n minus n naught x of n minus n naught. This is what we get. And here for x to same input I feed, what happens here first? X of n minus n naught shifted already. After that, I am applying the system operator. So what do you get? You get r raised to n x of n minus n naught. Now just check y1 and y2, are they equal? They are definitely not equal. These are not equal because here it is r raised to n, here it is r raised to n minus 1. These are not equal. Therefore, the system is time or not a time invariant, or else you can write time variant. It is varying with a time operator. That's an example for time invariance in discrete time domain. I hope it is clear to you. Now we'll quickly go to the next property of the system and the last property of the system, that is linearity. A system is said to be linear in term of the system input excitation x of t and the system output response y of t if it satisfies the following two properties. The meaning is, the system is said to be linear in terms of system input x of t and system output y of t if and only if it satisfies the following two properties. What are those two properties? One is superposition properties and the second is homogeneity property or scaling property. Always remember, for input, system input, we call it as excitation. Input is also same, excitation is also same. System output is also called as response, system response. Remember this. Interchangeably we use input and excitation, system excitation or system input, and system output for system response. Okay. Now, before we proceed, we'll understand what's the principle of superposition, what is the principle of homogeneity. So, to understand superposition, let us go through this statement. Think that the system is initially at rest. When system is at rest, the input is x of t is equal to x1 of t, and the output what we get with this input is y of t is equal to y1 of t. Next, for the next case, we apply the input as x of t is equal to x2 of t. This is suffix, okay? x2 of t. This is suffix x2 of t, and the output what we get is y2 of t. Then for the system to be linear, or else the principle of superposition tells that the composite input should produce corresponding composite output. So when I applied x1 of t, I got y1 of t. When I applied x2 of t, I got y2 of t. Let me write it here. When I apply x1 of t, I got the output as y1 of t. When I applied x2 of t as the input, I got the output as y2 of t. When I apply composite of t, composite means x1 of t plus x2 of t. Composite, this is called composite. I should get y1 of t plus y2 of t. So if this happens, then if this get produces just here, that is x1 of t plus x2 of t should produce the corresponding output y1 of t plus y2 of t. This is called principle of superposition. Remember this. Okay, and principle of homogeneity says, or scaling says, the system is initially at rest. If input x of t results in y of t, the system exhibits the property of homogeneity if x of t is scaled by constant factor called a, results in output y of t is scaled by exact constant a. Just check here, it is for your understanding. X of t produces y of t as output. A into x of t should produce the same scaled output a into y of t. 1 by a of x of t should produce 1 by a of y of t. So this is called principle of homogeneity. property of homogeneity. Both superposition and homogeneity should hold good for the system to be called as linearity. So this system, in the contrast, when a system violates either of this, that is principle of superposition or homogeneity, then it is said to be a non-linear system. Remember this. So to put in front of you in a mathematical model, let me take an example. So here I read it. When a system violates either of the principle of superposition or homogeneity, it is said to be non-linear. Now I am taking an example, x of t. So here it combines both homogeneity as well as superposition. For example, a is a scaling factor, so homogeneity I am testing, and summation is a sum of or composite signal. If n is equal to 2, I equal to 1 and 2. So a1 x1 of t plus a2 x2 of t. So it both checks superposition as well as homogeneity. That's why I took this. Okay. So now a simple system we are taking, we have to check whether the system is linear or not. So how to do it? Just check. So y of t is equal to what? H of x of t. And what is x of t here? It is given as h of summation I is equal to 1 till n ai xi of t. Okay. So this is nothing but h summation I is equal to 1 till n ai, I'll take it outside, h xi of t. This should hold good. This is nothing but h, sorry, I should have not written this. So h is taken care already. So what else we need to write is summation I is equal to 1 n ai. What is the h of xi of t? It is y of I of t. So this is what it should result in. So if a system is linear, then it should hold y of t is equal to summation I is equal to 1 ai y r of t. So this is a condition for system to be linear mathematically. Where what is yi of t? Yi of t is nothing but h of xi of t. So y1 of t should result in x1 of t should result in y1 of t, x2 of t should result in y2 of t, x3 of t should result in y3 of t. That's the meaning of this. And then similar scaling should happen at output also. That's the meaning. Okay. So to diagrammatically show this, let me draw it here with a different ink so that it will be much more clear to you. So here, first case I'll write it here, second case I'll write it here. So think that I have three inputs, x1 of t, x2 of t, x3 of t. Now initially I scale it. How to scale it? This I scale it with a1, this I scale it with a2, this I scale it with a3. First I scaled it, homogeneity. So after scaling, what I do is I add all these things. Summation for superposition. If I add it, what do I get? So I get composite signal. Now I apply it to the system. So it will result in y of t. This is first case. The second case being, I'll write it here. I have three inputs. First, I pass each of these inputs to the system operator. Then what I do is each one of the output I scale it. A2, this one also is scaled A3. Then after that I sum it. So whatever I get, that is my y of t. So in these two cases, the variation of the signal, the output of the signal should result in same manner, whether that is happening or not. Let us check it. I change the ink. So here a1 into x1 of t, a1 into x1 of t, this is a2 into x1 of x2 of t, this is a3 into x2 of t, x3 of t. How it is written with a summation? It can be written as, when I add all these things, it can be written as summation I is equal to 1, maximum is n value is 3, I is equal to 1 means this, I is equal to 2 means this, I is equal to 3 means this, ai xi of t, that's the meaning. So here I get this signal. Now for this signal I am applying it to the system. I am applying it to the system, and whatever the system gives, that is the output. Y of t is h of summation of ai. This is what I have written here. H of this one. H of this one. This is equivalent to this. That is what I want to show. Just check here. x1 of t, after passing on to the h, what I get? y1 of t I get. Here I get y2 of t. Here I get y3 of t. So when I scale it, what do I get? a1 y1 of t. Here I get a2 y2 of t. Here I get a3 y3 of t. So when I sum it here, what do I get? Summation I is equal to 1, I is equal to 1 till 3 ai. Here I am having yi of t. Correct? Yi of t. So that is what is here. This is what is equal to this. We call it as y of t. So for the system to be linear, this block diagram should not result in two different outputs. It should result in same output. Then only we call it as a linear system. I hope it is clear. Okay. So always a graphical explanation is preferred to be more convincing one. That's why I took the block diagram also. Okay. So now we will have one example for understanding the DTS signal of linearity. Okay. So solution for this. So the given signal is y of n is equal to n into x of n. We need to check whether the system is linear or not. So first, x of n is equal to summation I is equal to 1, I is equal to 1 till n ai xi of n. Okay. So here the meaning is a1 x1 of n plus a2 x2 of n, and it proceeds. That's the meaning. That's the meaning. I am just writing its meaning. Now I apply the system. Y of n is equal to h of x of n. The meaning is I have to apply this. So what do you get? N into n is a scaling factor kind of thing. I'll take it here. So summation I is equal to 1 till n ai xi of n. ai xi of n. Okay. So this is as good as writing summation I is equal to 1 n here ai n x of xi of n. Okay. So here you can check whether the n is scaled before adding or after adding. It does not make any difference. That's why you can diagrammatically again check. Hence y of n can be also written as 1 n ai. So n xi of n summation togetherly I can write yi of n. So therefore the output in each case is acting, it is giving the same output. Therefore the system satisfies homogeneity, that is scaling, and superposition. Therefore it's a linear system. Okay. I want you people to check it with a block diagram concept in this fashion. Only thing is you have to introduce n there. If you introduce n in the same fashion, you'll get the same output. You can check it at your end. So by this we declare it as a linear system. We have two more such examples. We'll solve it. So 2 raised to n x of n, whether it is linear or not, that we need to check. To check its linearity, what we do is I'll just prefer this one. I write it as h of x of n. This is a system. Okay. So summation, uh, what we do is x of n, we call it as summation I is equal to 1. Let me take, for simplicity, I call n equal to 2. ai xi of n. Okay. So this one can be written as um, I apply h of x of n. Means, how can I apply it? H of x of n means a1 x1 of n plus a2 x2 of n. So this will result in what? So I made it very simple for you. This is nothing but y of n. So this will result in, so what we are supposed to do? H means what? H means applying the system operator, what it is doing? It is multiplying 2 raised to n. 2 raised to n, 2 raised to n, a2 of x2 of n. So what do you get? You get it as a1 2 raised to n x1 of n, a2 2 raised to n x2 of n. This is 2, okay? N, this can also be written as a1 h of x1 of n, a2 h of x2 of n. So separately I can write a1, this is y1 of n, plus a2, this is y2 of n. Very simple, right? So I can get in this fashion. This is what is a superposition and homogeneity principle. Hence the system is linear. System is linear. Now similarly for this one, I call it as h of x of n. So now h of summation, this one I apply ai xi of n from summation, this one same way, a1 x1 square of t plus a2 x2 square of t will result in a1 x1 square of t plus a2 x2 square of t. Okay, so this is equation number 1. Now what we do is, now first I add it, for example, a1 x1 of t plus a2 x2 of t. Now first I am adding it, and then I am applying the system. So if what is the system operator? System operator is squaring. If I square it, what happens? a1 x1 of t plus a2 x2 of t whole square. So it will result in what? Will it result in the same way? No, definitely not, because it is a plus b whole square. A square plus b square, that is, this is a square, this is b square, plus 2ab. 2ab will also be added to this. Hence 1 is not equal to 2. Therefore system is non-linear. System is non-linear. So these are the two examples for linearity, and one example I took for non-linearity. This is being the last property of the chapter or the system. This concludes your chapter number 1. Few questions from the past exam paper are most favorable questions for the practice and use as a tutorial. That is what I'll be considering now. So here, sketch and label each of the following signals. X of t is equal to u of t minus u of t minus 1. What is u of t? U of t is unit step. It is unit step, right? What is u of t minus 1? U of t minus 1 is shifted version. It is a step is shifted at 1. Continues. So if I subtract u of t minus 1 with u of t, what happens? Till 0 to 1, there is no signal, it will continue. After 1, there is a signal 1 with amplitude 1. Here also amplitude 1. It gets cancelled. So you will result in a step signal in this fashion, which will result in a rectangular pulse from 0 to 1 with amplitude 1. Okay, so this is x of t. Simple thing, right? We have understood it already. Now there is a delta function. So delta function you already know. So it's a delta function or an impulse function with strength 1 at t equal to 0. Okay, this is a delta function. Delta of t minus 3 by 2 means shift right by 3 by 2 times. Shift the same signal by 3 by 2 times. It has been shifted. Actually, it should be amplitude is 1. Amplitude is 1. Okay, so quite a easy signal. Amplitude or area is 1. Now I have a problem here. G of t is given. G of minus t minus g of t, g of t minus 1, g of 2t. All these things you need to do. This is the reflection. This is a negative amplitude. This is a shifting. This is scaling. We will do it. There are two different signals given, A and B. So we'll take it in the next signal. So A and B separately we'll solve it. For the simple right angle signal, if I apply a reflection g of minus t, g of t minus t means divide by minus everywhere. That's the meaning. Minus means it becomes minus 2. So reflect it minus 2. This is how it looks. Okay. And similarly, g of minus t, if I do for this, it will be reflected version. So whatever happening at 1 will happen at minus 1. Whatever is happening at minus 1 will happen at 1. Just fold it. So if you fold it, so this will look in this fashion. This is 1, this is minus 1. Right? So at minus 1, it is rising and it is coming to 0. At 1, it is, it is coming to 1 from rising edge. So it is just a reflected version. Minus g of t means fold it with respect to x-axis. Amplitude scaling it is. Minus 4. Minus 4. Here it is minus 2 time scaling. Here it is amplitude scaling. Minus 4. So minus 4 it is. And here it is just reversing. You bring it down here, this you take it up. Okay, that is what is happening in minus g of t. Now shifting by one time, shift it by one time, 2 goes to 3, 0 goes to 1, 1, 3, you get this. And similarly shift it by one time, so minus 1 comes to 0, 0 goes to 1, 1 goes to 2, 0, 1, 2. Okay, similarly if I time scale it by 2, divide by 2, so if you divide by 2 you'll get it as 1, 1 here. If you divide by 2, minus 1 by 2, 1 by 2, minus 1 by 2, 1 by 2, compressed version. So compressed version. Simple, very simple. Now we have a lot of other signal here. Please concentrate. It's like puzzle solving. G of t is equal to 2 into u of 4 minus t. So all these 8 examples I'm taking it here. G of t 2 into u of 4 minus t, or else you can also write it as 2 into u of minus t plus 4. This will be easy for us, right, to analyze. What is first? It is having scaling as well as shifting. What should be done according to the precedence rule? So precedence rule says you need to first shift, replace minus t with t. So u of t plus 4. U of t plus 4 means what? U of t plus 4. I'll write it here. You know how u of t looks. So shift it by 4 times onto the left. This is u of t plus 4. Now for this, I'm scaling it by minus. I'm reflecting it. Minus. So divide by minus means what you get? You get 4. Whatever is happening at 4, minus 4, it will happen at 4. So it is reflection version, reflected version. Fold it. If you fold it, minus 4 overlaps on 4 and it will come in this fashion. Folded version. Folded version will come in this fashion. Okay, of course the amplitude is here. If I take it as 2, amplitude 2, this becomes amplitude 2. Folded version will look in this fashion. So I can set such a number of examples. G of t is equal to u of 2t. You know that u of t looks like this. Okay, if I time scale it, 2 0 divided by 2 will also be 0. So same looking u of t will look in the same manner of u of 2t. See, it is just to confuse you people. Both mean same. Okay, that is what is g of t. It is written here. Now what is SGN? SGN is a signum function. Signum function looks like, signum function was looking like, if you remember, this is plus 1, this is minus 1, continuing. This is how the signum function was looking. Now amplitude scaling is phi. So make it as phi here, amplitude scaling. But it is shifted by 4 times onto the right. This is 0, shifted by 4 times. What do you get? This change, this pulse will move by 4 times. That is what is here. Move by 4 times. That is what is here. Now this one, I want you to take it as an assignment. I have explained you how the signum function can be shifted. So the hint is 1 plus SGN minus T plus 4. Please give importance to the precedence rule. So this is a signum function, 1 plus signum function with shifted and scaling both. Apply precedence rule, take it as an assignment, do it by yourself. It's a question mark. Now, g of t is equal to ramp function. You know that how the ramp function looks. Ramp shifted by left. If I ask you to write a ramp function shifted by left, how it looks? This is how it looks. Now, amplitude is 1 here. Amplitude is 1, okay, because slope is 1. If I scale it by 5, amplitude 1 becomes 1 into 5. It becomes 5. Slope will be increased. Now you have to shift it. Same thing is given here. Where is it? E. 5. It should be 5. Yes, it is correct. It is 5. And at 1, it will be 10. Same thing. I had drawn it in the same manner. Okay. This is at 0. At 1, what happens? At 1, it should be 2. 2 into 5 is 10. It should be 10. The same thing is drawn here. And similarly, ramp function, if I scale it by 2, what happens? R of t is like this. At 0, at 1, you have 1. And if I scale it by 2, what happens? This becomes 1 by 2. At 1 by 2, your amplitude is 1, right? So now I am amplitude scaling it by minus 3. Minus 3. So if you just multiply it by minus 3, here you will get minus 3 at half. At half you get minus 3. And at 1, what you get? At 1 you get, here you are getting 2. So at 1 you are getting minus 6 here. 2 into minus 3 is minus 6. This is minus 3 ramp of 2t. Now 2 delta plus 3. This is area scaling. 2 is done. 2 is taken care. Shift it by 3 times onto the left. Shift it by 3 times onto the left. Delta is shifted by 3 times onto the left and its area is scaled by 2. That's it. You know how delta function looks. And similarly here, so let me write it. First, you need to do delta of t plus 9. Shift it first. So what do you get? You get it at minus 9, 1. It is 6 times area scaled, 6 times. So I write it as 6. Now, delta of 3t I need to do. That is time scaling. Divide by 3. So divide by 3 gets you what? Minus 9 by 3 is minus 3. That is what is minus 3. Amplitude is 6. That's it. This is h. Okay. Similarly, you can have n number of examples. I am having some discrete time functions here. U of n plus u of n minus n. U of n is, here you have a signal, here you have a signal, here you have a signal. Continuously it will go on. U of minus n is folded version of this. Here you have signal, here you have signal, here you have signal. Minus 1, minus 2, it goes on. If you add these two things, everywhere you will be having amplitude 1. That is what you, g of n. And u of n, if you subtract it, minus if you introduce here, what happens? It is amplitude. Amplitude is taken in negative. Here you have signal, here you have signal, here you have signal, here you have signal. Okay. So this and this, if you consider minus 1 here and plus 1 here. If you subtract here, this at 0, it goes to 0. And rest everywhere you have this signal. And for positive axis, you have u of n signal, this signal, and you have this signal. This is g of n for u of n minus u of n minus 1. Okay. So you can have a number of such examples. G of t, 3 into delta of 3t plus 6 into delta of 4 of t minus 2. Remember one thing, for delta function, strength is 1. If you scale it, time scale it by any number, let it be any number. If you 0 divided by anything, will result in same thing. this is equivalent to delta of any scaling of time scaling. We had learned one property, that is delta of AT is equal to 1 by A into delta of T. I hope you remember. So this property we had learned. So hence I had forgotten to just add it. Please look here carefully. So this 3 into delta of 3t will result in what if I apply this? In place of A, what I am having? 3 I am having. 3 into 1 by 3 delta of 3t. Okay. So delta of just t. Delta of just t. So what do you get? You get delta of t. Hence in place of 3 into delta 3t, I am writing delta t. So I'm writing delta t here by the property. I'll write it once again here because of this property. Similarly, if I apply this property here, so what do I get? I get it as delta of 4 t minus 2 will result in 1 by 4 delta of t minus 2. So this 6 by 4 result in 6 by 4 delta of t minus 2. So 6 by 4 means 3 by 2. That is what we got it here. Okay. Delta of t, write it first here, plus delta of t minus 2 means shifted by 2 times. I am having here amplitude is or area is 3 by 2. Write it as area is 3 by 2. I hope there is no doubt. Okay. So next, I want you people to take it as an assignment because this is a special example. Delta suffix 1. Suffix 1 means what? For that I am giving hint. Suffix 1 means summation n is equal to minus infinity to plus infinity delta of t minus capital T n. I hope you remember this. This is suffix. Here I am having 1. So I am writing 1 here n. So in place of t I am having minus t by 5 minus t by 5 minus n. So this is sign. This is impulse train. If you don't forget, impulse train. Just write the impulse train, scale it by 5. Just tell me what you get. So this also you take it as an assignment. So next, this is x of t. X of t is minus 4 of t. So and this is x of minus t is replace t with minus t. What do you get? You'll get 4t. Now minus of x of minus t is, this is what is that? You will get minus 4t. You will get minus 4t. So x of t is 4. Here you get minus 4 of minus t will get 4t, 4 of t, and x of minus of x of t is minus 4 of t. Okay, so minus 4 of t, if you draw it, so what do you get? X of t is minus 4t and x of minus t is 4t. This is 4t, this is minus 4t. So hence it is not equal, x of t is not equal to x of minus t, hence it is a odd signal. And if I draw it in this way, it looks, this is even and odd. This is even and odd. Similarly, you can have any function for asking whether it is even or odd. E raised to minus of mod of t. So mod of t, mod of minus t is also in the same fashion, it is positive itself. It is as good as e raised to minus of t itself. Hence, this is a even signal. Okay, and cos t is a even. Hence, scaling of cos or time scaling of cos will result in even signal itself. That's a fundamental. Sine of 3t minus pi by 2. So this is written as, if I take minus outside, I get pi by 2 minus 3t. This will result in minus cos 3t. So cos 3t is a even signal. Of course, it is amplitude scaled with minus, so it will be inverted, but it is a even signal. Hence, it gives in an even signal. Please don't come to the conclusion by looking sine signal directly and write it as odd. Okay, sine is odd, but here it is pi by 2 minus 3t. So it results in cos. So cos is a even signal. It's a even signal. Okay. Similarly, you can try for u of t, whether it is even and odd. So u of t is like this. So it is neither symmetrical nor anti-symmetrical. Hence, it is neither odd nor even. Remember this. U of t is neither odd nor even. 1 mark question. Okay, so you can have can take this as an assignment. You can just scroll it. I'll share these ppts to you. You can solve it, and answers are there for your reference. 10 sine of 20 pi t, check for even and odd part. As sine is there, it is a odd signal, so even signal will be 0. It is whole of things is odd. Similarly, you check for the even and odd for all the given signals here. This one, this one, this one, this one. Take all these as an assignment. Cos pi t by pi t, sine 4 pi pi t by 4 pi t. This is like a sinc function. Okay, so average signal and power signal calculations. This you here you need to compute average and power signal. Wherever it is infinite signal, go for power signal. It is infinite signal, power signal, infinite signal means it'll till infinity it is u of t. That amplitude is 1. So you should calculate average power. Answers are given. Please compute, match it with your answers. So average signal. So sum of the energy signal 2 into rectangle of t. So find out it's a rectangular pulse with amplitude 2. Find the energy of it and find it. So there are some assignment for you on the linearity, on the properties of the system. Take it as assignment. This is a given question. N into x of n minus 1 plus 2. Check whether it is memoryless, time invariant, linear, causal, and stable. Okay, so invertibility is not taken here. It is not definitely not invertible. That's why. So x of n into x of n minus 1 plus 2 is a system given. Check for all the properties and come up with the answer. So one more, x square of n minus 2 and odd signal, any odd signal, it is odd signal of x of t. Check for linearity, time invariant, or both. This is also a assignment for you. So all these are assignment for you. Wherever I have written assignment, you need to do it, cross check it with the answers if the answer is given. If answers are not given, come up with your answer. Let me just verify whether it is a correct answer or not. Okay, so with this we are concluding the chapter number 1. So what are the outcomes that we achieved? The outcomes achieved are, we could able to understood what is the signal and the classification of the signal. We had around 5 classifications. We understood each of the classification. Those are continuous time, discrete time, even odd, then periodic, non-periodic, deterministic and random signal, then energy and power signal. All the 5 classifications we could understand, and we could understand some signal operations, amplitude, on dependent variable and independent variable, that is amplitude scaling, addition, subtractions, integration, differentiation, all those things. And in time scale, time independent variable, it is time scaling, time shifting, folding, precedence rule, all those things in both discrete time and continuous time. This also we studied, and also we understood what is the system and its properties. 6 properties. Those properties are linearity, memoryless, time invariant, linear, causal, stable, and invertibility. And then we could solve many examples, many problems. Okay, so with this we are at the end of the chapter number 1. Thank you. If any queries, feel free to post your questions in the YouTube comment section, or you can contact through my mail IDs. Thank you.